Hey guys, what's going on? We're going to do the homework, the extra homework here. A little video for you just to make sure you guys are doing well and understanding these problems. So let's just jump right in here. We got Rhonda Mulberry Bush kicks a can of Cheese Whiz horizontally. Alright, so it's a horizontal launch problem at 4.6 meters a second off a cliff, 12.4 meters high. How long will it take to land, and how far from the cliff will it land? Right, so how long and how far? Looking for here. Excuse me. So it is a horizontal launch. So I'm going to draw a little diagram here. Ball, Cheese Whiz can, whatever. 4.6 meters a second, and 12.4 meters high. Okay. Now we said earlier in class that we can use a shortcut equation. This guy right here. If and only if the object is launched horizontally or dropped. Well, lucky for us, this is a horizontal launch problem, so we can use this equation to find our missing variables. We know what the height is. We know what g is. Y'all can just use 10 as g for this worksheet. You can always assume g is 10 unless the problem tells you otherwise in this class. And then so we know h, we know g, that we can just solve for t, and that'll tell us how long it'll take to land. So we're just going to do that real quick. My calculator right here. Get that ready to go. So we're going to do the height of the cliff is 12.4 meters. So equal 1/2 g is 10. And then t squared. Half of 10 is 5, so 12.4 equals 5 times t squared. I'm going to divide by 5. Both sides. T squared is going to be 2.48. Square root both sides, cancel that squared sign there. I want t, not t squared. And I'm going to get 1.57 seconds. Alright, so that's the first part of the answer. How long? 1.5 seconds to the ground. How far from the cliff will it land? How far from the cliff? Not how high will it go, but how far from the cliff will it go? That's called a horizontal distance, right? So when we're talking about horizontal distance now, we're going to use the horizontal velocity that we're given initially, and we're going to remember that x equals vt is all I need for horizontal motion, right? V is my velocity, 4.6. Now I know that t is 1.57. I'm going to plug that in, and I'm going to find out how far it goes horizontally. And that's going to be 7.24 meters. And there you go, that's it. Fairly straightforward, so not too bad. Alright. Alright, let's go to the next problem. Struggling with a fire hose, Jean Zahn, weird name, aims a stream of water vertically up. Alright, so it shoots the water straight up in the air at 17.3 meters a second. How long, that's time, right? How long something takes is time. How long will it take before the stream is falling at 8.8 meters a second? So we're looking for when the velocity final is negative 8.8. And why did I put negative? Because it says it's falling. Falling means negative, going down, right? So we're looking for negative 8.8 meters a second velocity. Our initial velocity is 17.3. So what do we know? We know initial velocity, if not 17.3. We know this is vertical, by the way. That's all vertical. There's no horizontal motion at all, right? She launches it straight up in the air, so it's not going to, there's no wind blowing, apparently, so nothing to worry about horizontally. So initial velocity, 17.3. Final velocity, negative 8.8. We're going to find out how long it takes to get to that point. We know the acceleration due to gravity is negative 10. We're looking for the t. Don't know what t is. But with these equations, these variables, look at my equation chart on the left here. Looks like I can use this first one to find out my t, because I know final velocity, again, negative 8.8. Initial velocity, 17.3. Plus a is negative 10 times t. I'm going to solve for t, so I'm going to subtract subtract 17.3 from both sides. And I'm going to get negative 26.1. T, I'm going to divide by negative 10, and I'm going to get a positive 2.61. So there you go. That's all it takes. Alright, and another hard part is picking variables and equations, but hopefully the actual practice is doing you good and you're starting to get it. So let's keep going to the next one. The soccer ball is kicked vertically at 20 meters a second. Alright, so we're vertically up. Oh, guys, that's terrible. Up arrow, isn't it? Jesus. Fix that real quick. Ah. That's my pin. Okay. Straight up. Oh my god, what's wrong with me? I think I have some sort of condition where I can't draw straight lines on this pad I have. Alright, one more time. Here we go. I got this. I can do it. That's pretty good. Bad arrow, but whatever. Okay, so kicking straight up in the air, 22 meters a second. How long will it take? That's time, right? Looking for how long something takes. That's time. So we're looking for t. Will it take to reach the peak of its flight? What do we know about the peak of the flight? Remember, it goes up. This is the peak, goes back down. We know that special spot at the peak, the velocity, the vertical velocity at that spot is 0. So that's going to be our final velocity, 0. Our initial velocity was 22. We know acceleration is negative 10. We're looking for t. Same equation. Plug it in. Bada bing, bada boom. 0 equals 22 plus negative 10 times t. Negative 22 equals negative 10t. T equals 2.2 seconds. Piece of cake, right? Alright. Next one. Alright, this one's kind of like the one we were doing in class, actually, so make sure you're in degree mode when you go to do these problems. We got Sammy Sosa. You can tell this was written back in the 90s, I think, because who knows who Sammy Sosa is anymore, unless you're a baseball fan. Alright, so excuse me. So it's going to leave this baseball bat. So I'm going to draw the vector here. So 76 meters a second. And we have our components. We should always find components first. That's going to help us a lot. This angle is 57 degrees. I did not draw this very accurately. It should have been more like this way, but whatever. Just a drawing to help us show the diagram, so it's okay. Alright, let's find our components first. Make sure we're in degree mode. I'm in degree mode. So 76 times the sine of 57, and I'm going to get 63.7, so my vertical component is 8.7 meters a second, and 76 times a cosine 57, my horizontal component is 41.4 meters a second. Okay. Now that I have my components, I'm just literally going to scratch this out. I don't want to be tempted to use it anymore. I don't care about you. Go away. That's all I need is my components. Alright, what do we know here? So, how long is it in the air? Is looking for how long is it in the air? Okay. Assume his bat is 1 meter above the ground level when it contacts the ball. Okay, so our initial position then is 1 meter, our initial height. We're looking for t. We have an initial velocity of initial vertical velocity of 63.7. We know that when it gets to that special spot in the middle there, right, this peak point, the velocity here vertically is 0. So remember, we can use that, right? So I'll do the technique we talked about in class where multiply by 2. Oh no, wait, I can't, can I? Oh, because look, I'm 1 meter above the ground, so I'm not landing at the same place where I launched from. So I can't do the whole times 2 strategy we talked about in class. I gotta do it the way we did the problem with the marble launcher in class. So, alright, so we're gonna find out, okay, how long does it take to get to this spot here? How long does it take to get to there? At that spot, my velocity is 0, so I'm gonna use this first equation here. Velocity 0 equals my initial vertical velocity, 6.37. 63.7, I mean, plus a negative 10 times t. And I'm going to get t equals 6.37 once I do a little algebra there. Alright, so that's my t. That's to get to this high point, right? Not for the whole thing, just the high point. Now, how high does it get? Alright, for that I'm going to use a second equation. Okay, so how high does it get? That's x equals, my initial position is 1, plus my initial velocity, 63.7, times the time, 6.37. That took that long to get to the peak, right? Minus 1/2 times 10 times t squared. I went ahead and put the minus here instead of by the 10 because we know we're gonna subtract that anyway, right? Okay, so let's do t. Oh shoot, what was t? T was 6.37. So scratch that out. Times 6.37 squared. Okay. All right. So we get our calculator. We just punch it all in there. So I'm gonna do that real quick here. 7 squared times 5, and then 63.7 times 6.7 minus that. So I got 203.9. So what is our total height then? We 203.9. 203.9 meters of total height. How long will it take to fall from that point? Remember, once we get to this peak position, we're basically a vertical launch, or sorry, a horizontal launch problem. So we can use the shortcut h equals 1/2 gt squared. My total height now is 203.9. 203.9 is 1/2 times 10 times t squared. So I'll divide that by 5 and then square root it. Then I get 6.38, 6.4, let's call it. So t is there, it's 6.4. This is how long it takes to fall from the high point down to back to the bottom, to the ground. You'll notice it's very similar to our initial time from here to the high point. And they're so similar because our initial height was only 1 meter above the ground, right? So it doesn't take very long to go 1 meter when you're going up at 63.7 meters a second. Alright, so, yeah, that's it. We're going to add them up now. That's all I wanted to know was how long it's in the air for. It didn't ask us how far it goes, so that's cool. So 6.4 plus 6.37, we add them up, and we get 12.77 seconds. And that's it. That's our time. That's how long a ball is in the air for. I don't think it asks us to find anything else, did it? How long is it in the air? And no, that's it. Okay. Cool. Let's go to the next one. Projectile is fired vertically up. Alright, so normally it's vertical up. Firing is 35 meters a second, vertically up and straight up in the air. How long will it take to reach a height of 40 meters? Alright, so now we're going to know when the height is 40. What are the meanings of each solution? We'll figure out, talk about that in a second. Alright, so what do we know? Initial velocity, 35. We don't know final velocity, do we? But I do know what our initial position is, 0, the ground. I know my final position wants it to be 40. I don't know how long it's going to take to get there. I do know acceleration is down at -10. I'm looking for time. How long will it take? It's time. So I want to find t. Okay, so it looks like I have enough for this equation number 2 here. Got x naught, a, looking for t, v naught. Yep, looks good. I can do that one right. So x is 40. 40 equals x naught is 0. That's my initial height is 0. So 0. V naught is also 0. Oh no, sorry, no, just kidding. It's 35. Just kidding. Oh, I just realized we could use a bottom equation. No, we can't because somehow that's going. Just kidding. Okay. Spacing out 35 times t, which we don't know. And then we're going to do plus 1/2 times a is 5, so I'm just going to write 5. Or, sorry, minus 5, shouldn't it be? Should be minus 5, sorry. Because we know that that's going to be a positive. I mean a negative. Minus 5. And then, let's see, times t squared. Alright, I'm going to do a weird thing here, guys. I'm going to subtract 40 back onto the right side of the equation. So it'll be 0 equals 30. I'm sorry, erase that actually. I'm going to set it up a pretty good way here. Alright, so negative 5t squared plus 35t minus 40. Why did I set up this way? Think about this for a minute. It asks us about the meanings of each solution. It implies that there's going to be more than one solution. There is, because when the ball is fired up, it gets to a 40-meter height, but then it keeps going. And then it comes back down, and it's at 40 meters again on the way down. So it actually goes through the position, and it has the height of 40 at 2 different times, right? Hopefully, you remember your algebra class, and this looks familiar to you. This is a quadratic formula setup, right? We have our A term, our B term, and our C term. And the formula for the quadratic, which you will not get on a test or the AP exam or my exam or any exam or quiz or anything. So if you're ever going to use it, you have to know it, right? And it is x equals the opposite of b plus or minus square root of b squared minus 4ac divided by 2a. You said, I learned that when I was in like 4th grade. We said it to the tune of Row, Row, Row Your Boat, and I've never forgotten it since. So x equals the opposite of b plus or minus square root of b squared minus 4ac divided by 2a. Your a term is always the coefficient in front of the variable that's being squared. The b term is the coefficient in front of the term that's not being squared. And then the c is always just a constant, the one that has no variable with it at all. Right? So I'm going to pause the video just for a second. And we're back. Sorry about that. Alright, so I'm going to set this up for you here. So x, and really I shouldn't put x. I should really write t here, right? Because it's not solving for x, it's solving for t. T is a variable that I am looking for. It's the one that's we don't know. There's 2 of them, and they're both a t, but one's being squared and one's not being squared. So the only real way to solve this problem is to use a quadratic formula. So t is going to equal the opposite of b. Well, b is 35. It's the opposite of b, right? So it's negative 35 plus or minus. We're doing plus or minus because there can be 2 answers, right? There's going to be 2 answers, so we do plus or minus. One time we'll add all this stuff under the square root, and the other time we'll subtract it, and that's how we get the 2 answers. So square root of b squared. B again is 35, so 35 squared minus 4 times a. A is negative 5 times c, which was negative 40. Off the screen there, so I hope you can see that. Okay, it's a negative 40. Okay, and then that's all that's being squared. All that. So what I usually do in these problems is I solve whatever's under the square root sign first, and then I go from there. And then on the bottom of the fraction is 2a. Well, a is negative 5, so 2a is negative 10. All right, so that's a setup for you, right? And I'm going to tell you what the answer is. So I want you to try it, though. Plug in your calculator, see if you get the right answer. The right answers are, there'll be 2 of them, right? Because they're going to have 2 answers. First one is 5.56 seconds. And then it's also going to be that height at about 1.44 seconds. So if you didn't get those numbers, try again. And just be careful with parentheses. When you do this over here, I would do, you can just do negative 4 times a negative 5 times a negative 40, right? And then take that number, whatever it is, and then do plus 35 squared. And that should get you, and then square root that, and either add it or subtract it to negative 35, and then divide by negative 10. And you should get these 2 numbers here. So these are the times at which the object will be at 40 meters height. 2 different times because it's one on the way up and then one on the way down. Right. A disgruntled fast food operator hurls an Egg McMuffin at 18 meters a second at 26 degrees from the horizontal. So our initial velocity 18 meters a second. We're going to get a horizontal and a vertical component. 26 degrees is my angle. So I'm going to get my calculator and I'm going to see what my components are. Always the first thing I do. Check, make sure I'm in degree mode. Yep. 18 times the sine of 26 is 7.89. So I use sine as my vertical component. And then 18 times the cosine of 26 is 16.18. meters a second. So, okay. There we are. Got my components. Alright, what am I looking for here? Oh, he's on a cliff, 12 meters high. Okay, so he's up in the air. Alright, he's 12 meters high. And he's shooting this. Oops. He's shooting a Egg McMuffin. Huh. What a waste of an Egg McMuffin, right? Let's see. My eraser here real quick so I can delete that. Just that line there. Alright, so top of the cliff. Shoots it. And these, I'll do the components already, so I won't draw it again up here. So it's going to go down, it's going to go on the ground. Asking us, what are its initial horizontal and vertical velocities? Well, I just found that. Right, vertical, there's horizontal, done. How long will it be in the air? Alright, so here we go. Now, guys, two ways to do this, okay? I'm gonna do the one I like better. I think it's shorter and less steps, but it might be more complicated. We already know, you know how to do the one that we've been using already, right? You're going to find out, or rather, you know what the velocity, vertical velocity is there, right? You know what it is. It's V naught here is, or sorry, not V naught, V y there is 0. You know the initial vertical velocity. You can use this equation here to find out how long it takes to get up there, okay? And then you can use the second equation to find out how high it gets. And then you can use the second equation again, or really the shortcut, to find out how long it takes to fall down back down the ground once you know the total height. You add all those times up to get this part. But I'm going to show you how to do the quadratic formula version. Okay, we have enough information. We know the initial vertical velocity is 7.89, so V naught 7.89. We know the acceleration of gravity is negative 10. We're looking for t. We know what t is, and we know our initial position is 12, and our final position is going to be 0 because it's going to the ground, right? This is all I need for this middle equation. The problem is I'm missing t, and there's a t squared and a t. Alright, so, but again, perfect setup for a quadratic formula. So I'm going to set it up here. First, remember our quadratic formula. X equals the opposite of v plus or minus square root of b squared minus 4ac divided by 2a. Okay? I know I have a little singing voice, trying to be jealous. Alright, so we're going to set this up here. First I'm going to set up, I'm going to put in my numbers here. So my x, my final position is 0, equals, I'm going to go start with the squared term, so this is my a term. So 1/2 a. 1/2 a is negative 10, half of that's negative 5, so negative 5 times t squared plus v naught t. V naught is 7.89 times t. And then plus my initial position, which is 12 meters. So if I set up my a term, my b term, and my c term, so set up in the quadratic, it's going to be t equals opposite of b, so negative 7.89, plus or minus, we'll do it twice, square root, and I'll talk about that, because we're only going to get one answer for this one. I'll explain that in a second. Let's set it up first. B squared, b is 7.89, so 7.89 squared, minus 4 times a was negative 5, c is 12, divided by 2a. Again, a is negative 5, so 2a is negative 10. Alright? Now, when you do this under the radical first, all this stuff here, you're going to get a positive number, okay? But the number will probably be larger than negative 7.89. So if you add it, if the number under the radical is larger than the number you have out here, since it's negative, the one out here is negative, if you add the number under the radical to this, you'll get a positive number. But then when you divide by negative 10, you will get a negative t. You can't get it. A negative t is impossible, right? It can't happen. You can't get a negative t. So only one of these answers will give you a positive t, okay? And that's the one you want to use. And when you solve it, again, I want you guys to try this. Plug the numbers in, see if you can do it on the calculator. You should get t equals 2.53 seconds. All right? And the more you do this formula, the more you kind of get the hang of it, and you'll kind of start to know which either do plus or minus. You'll just kind of see it ahead of time and know which one to do once you practice some more. All right, and now that we know the time, and that's total time in the air. That's one step total. Well, granted, kind of a long step, but still, it's only one step. That's total time it's in the air. So there we go. So now we're going to do how long will be in the air, 2.53 seconds. How far from the cliff's base will it land? So we're talking about how far it's going to go horizontally, right? How far will it go horizontally? Not how high it gets, how far will it go from the base? So that's horizontal, so that's x equals vt. Simple equation for that. Now we know t is 2.53. My horizontal velocity was 16.18. And that's going to give me my x, and my xn will be 40.9 meters. So yeah, this answer, this guy here. Okay, so there you go. There's the quadratic formula that worked there. You learned that in Algebra 1 probably or something, and you thought you never used it again. Surprise! Okay. All right, let's move on to the back side now. I'm going to do number 8, or on the back it's number 1, and then number 3 first, and then I'm going to do number 2 last because it is a doozy. Okay. When we get to number 2, if you're still watching, you want to skip ahead to number 2 on the back side. That's just be patient and don't get scared. All right. Number 1 is pretty easy though. Soccer player kicks a ball horizontally off the edge of a 40-meter high cliff into a pool of water. All right. So, God, I just can't draw a straight line. Oh, that's a cliff. Whatever. Ball horizontally kicked, 40-meter high cliff. So 40 meters up from here down to the ground. Man, I have no widening that. I promise. I don't know why I can't draw straight lines. All right. Into a pool of water. So down here is water. Oh, let's make it look pretty. It's a pool of water, so I'm looking at my other. Why can't I do it? Oh, let me pick blue. Don't let me do it. Oh, let me do it. Okay, whatever. I'm over it. Hi. Okay. I don't know why I want me to pick blue. It moves. Alright, so anyway, where were we? Can I draw it? Can I draw it? There we go. Okay. Alright, sorry about that. So a pool of water down here. And it's going to go water. And it's going to make a splash. Excuse me. And 3 seconds. The student who kicks it hears the splash 3 seconds after the kick, right? And it's asking us what the initial speed was, and also gives us the speed of sound through air. It's 343 meters a second. Okay, so what's going on here? Well, first of all, whether or not we hear it land, it's going to land in a certain length of time, whether we hear it or not. And we know how long it's going to land because we can use our shortcut equation here, h equals 1/2 gt squared. We know how high the ball is, and it's kicked horizontally, so we can use our shortcut equation. So h is 40, 1/2 g is 10, and we're going to solve for t. And if we do that, we're going to get t equals 2.83 seconds. All right. So that's when it actually lands. But the student doesn't hear it until 3 seconds have passed. So what's happening in those 0.17 seconds that's left over, right? He hears it in 3 seconds, but it actually hit the water in 2.83. So what's happening is the sound is traveling during those 0.17 seconds, right? Where am I getting 0.17 from? 3 minus 2.87 is 0.1. Oh, sorry, this is a 3, not a 7. This is a 7. Sorry, I mixed them. Hold on, let me just fix it real quick. I mixed up my numbers there. So this is. Alright, so this was 2.83. 2.833. There we go. And this is okay. So that's where I got the 0.17 from, right? So there's this leftover time, right? That's the sound waves flowing through the air back to the student's ears to hear it, right? So if it took that far, or that long rather, for the sound waves to go back to the student, how far must it have gone? Well, we can figure that out, right? Because we know how fast the sound waves move. It gives us that in the problem. So sound waves do not accelerate. Okay, sound waves have no acceleration. They move at a constant speed. They're waves, and that's how they work. So x equals vt. We know t now is the sound waves are moving for 0.17 seconds, and the velocity of a sound wave is 343 in air. And so how far will they go? They will go whatever that is. 343 times 0.17, and that is 58.31 meters. Okay, so now we know how far the ball went. So now we just got to figure out how fast it's going. So if the ball goes 581.31 meters velocity, we don't know velocity yet. How fast did it go? But we do how long it took to get there. It took 2.3 seconds, right? So we take that number and put it in here. So how fast must it have been going? We divide by 2.83. And we get a velocity of about 20.6 meters per second. Right? There you go. There's your answer. So we had kind of, think about that a little bit, right? So that's a challenge. It's a little tricky question, but not too bad, I don't think. Hopefully you're able to follow along with that one. Let's do the number 3 in the back now. This is the daredevil one from the back of the worksheet. Daredevil shot out of a cannon at 45 degrees. Okay, so we know the angle, 45 degrees. To the horizontal with an initial speed of 25 meters a second. Alright, so we're firing 25. We have a 45-degree angle. And we can find our, first thing we're going to do is find our components. So calculator, make sure I'm in degree mode. 25 times sine of 45, 17.7. And this bottom will also be 17.7. The cool thing about whenever you get an angle of 45 degrees, once you find one of the sides, the other side is always the same. The vertical and horizontal are always the same components when you have an angle of 45 degrees. Okay. Alright, so it's asking us a net is located at a horizontal distance of 50 meters from the cannon. Alright, 50 meters away down here, there's a net set up. Some sort of, that's a terrible net, but you get the idea. It's a net. And it's 50 meters away. Horizontally. Alright. The question is, at what height above the cannon should the net be placed? So we know it's 50 meters away horizontally, but how high vertically should we place the net so that the daredevil hits the net and catches them, right? Okay. Well, this actually isn't too bad. We know a lot of stuff here, actually. We know the, let's see, we know the, we know how far it's going to go. It's going to go 50 meters. And we can use our horizontal equation to find out how long it's going to take to get there, right? So it's going 50 meters, and its horizontal velocity is 17.7. Remember, once we find the components, we don't need this anymore. Don't be tempted to use that. 17.7 times t. So how long will it take to go to 50 meters, right? That's what we're looking for here, right? So it's going to be, and we're using the horizontal. This is one of those rare occasions where we are going to use the horizontal stuff first to find t, because it gives us the horizontal distance, right? Usually the problem doesn't give us that, but this one did, so we're going to use it to find t. So 50 divided by 17.7 is 2.83 seconds. So now we know that the daredevil rather is going to get to the plane of the net somewhere in this region in 2.83 seconds. But how high will he be? Will he be on the ground? Will he be low to the ground? Will he be way up high in the air? How high will he be? We don't know. So we got to find the height. So we can use now x equals 1/2 gt squared plus v naught t plus x naught equation to find this. So we're going to plug in our numbers here. This is going to be vertical, right? I know it's an x, but we're talking about vertical here. It's position in the vertical. A little y there. All right, so 1/2 g. G is just 10. We can just use 10. So it's going to be or I should have put an a there, shouldn't I? Because it's a negative. We do want to include a negative sign. So it should be an a, not a g. So -5 times 2.83 squared plus our initial vertical velocity was 17.7 times 2.83 plus 0, because our initial height is 0. And we do all that, and we're going to get, hopefully, if you do that, you get an answer. Oh, don't forget that 1/2. Oh, I did the half already. It's -5. Once we get through all that, we get an answer of 58. No, sorry. Look at the wrong 9.99. So basically 10 meters above the. Basically 10 meters above the cannon. All right. Okie doke. So yeah, there you go. Hopefully that is making sense for you. I hope so. If not, just shoot me a message or something, or see me after class. All right, now this one. Okay. You know what? Let me pause this just for a second. All right, guys. Sorry about that pause. I had my PowerPoint crash and then start over again. All right. So this problem is gonna take a minute. Okay. So you have to watch right now, and this is totally like beyond the scope of the class. You will never get a problem that's this challenging, and this, involved an AP Physics 1 or 2 for that matter. I don't think, but this is a true college physics problem, though, I think. Most stuff we do is pretty high level, but this is kind of, next level, so to speak. So I'm gonna go ahead and do the problem because why not? But I don't want you to get discouraged. If you're like, man, I didn't follow it. Don't worry about it. It's not a big deal. You'll grow into it eventually. For those of you who are interested in engineering and stuff like this. But some of y'all are often asking me, hey, let's do more challenging stuff. So why not? Let's go crazy. All right. So we got a cannon. It's got a muzzle speed. That means launch speed, right? But when it comes out of the cannon, it's going at 1,000 meters a second. Right. So I'm gonna draw a little cannon here. The can. Jeez Louise, what is with my... I just can't draw. I don't know. Whatever. That's my cannon. Screw it. Oh my goodness. Okay, no, I gotta start over. This is too bad. Let me put my pad up on top of the desk, so not in my lap. Maybe that'll be better. That'll help me out a little bit. Let's see here. Okay. Yeah, that's a little bit, I think. Alright, so there's my cannon. Got little cannon wheels on it. Okay. Yeah, that looks kind of inappropriate. Okay, whatever. Alright. And then, so firing it at some angle, we don't know, at 1,000 meters a second. Okay. And it's going to use to destroy a target on a mountaintop. Now, the target is 2,000 meters from the cannon. Horizontally, so we go 2,000 meters this way, 2,000 meters, and 800 meters up, and here is the target, right? This is the spot where we want to hit 800 meters up in the air. Okay, at what angle, relative to the ground, should the cannon be fired? Ignore for air friction. Well, thank goodness we're ignoring air friction. Alright, so at what angle? Now I'll give you a hint ahead of time. There are actually two angles that we can fire at. If he fires it really high up, right, and it can come down on its way down, hit the target, that counts. Or he can fire it at a flatter angle so that it hits the target on its way up, right? So that's the two angles that are going to be you can find here. Now we're going to use a couple of equations. Now, really, what we're doing here is we got to figure out at what time or times is our horizontal position 2,000 and our vertical position 800, right? So the equations we use for horizontal position is x equals vt, and the equation we use for vertical position is x equals 1/2 at squared plus v naught t plus x naught. And those are the equations we're going to be using. All right. The problem is we don't know what the components are because we don't have an angle. We have no idea. The components could be, fire really shallow, really steep. We have no idea. That's a bum. Okay, it's a big bum. But that's okay because we have a thing called a brain and trigonometry and algebra and physics, and we can use this stuff to solve really hard problems like this. So what we're going to do is say, okay, well, I don't know what the angle is, but I know the velocity here in the horizontal should be equal to, so I'm going to rewrite this first equation here. It should be equal to, I'm going to call it v times the cosine of whatever angle I'm using times t, right? Isn't Just looking at my notes real quick. Isn't this another way of expressing the horizontal velocity, right? Alright, so I was just saying how v cosine theta is another way of expressing the horizontal velocity. Because remember, whenever we go to find the horizontal velocity, it's always the hypotenuse, in this case it's 1,000, or v, when I wrote down v, times the cosine of the angle. We don't know what the angle is, so we're going to leave it like this. Now, another way we could express the horizontal position equation, this x equals vt, is what if we do put some numbers in there? What if I said, okay, well, I know x, the position is 2,000. First, let's solve for t first. So t, divide by v cosine theta. So t is going to be equal to x divided by, let me kind of space this out better so it's more clear what I'm doing. I don't want to go look back at this and be confused or confuse anyone else. Right. So I'm gonna just divide by v cosine theta, right? So I want to get t equals x over v cosine theta, right? That's one way to express this this equation, right? Another way we could express it is, well, what is the x? If we put in a value for x, we know that the position horizontally of this object needs to be 2,000, right? It needs to go 2,000 meters horizontally. So I'm going to put in a 2,000 for the x, divided by v naught is 1,000. That's my hypotenuse, right? Put 1,000 for that, times the I'm running out of room. Cosine of theta there. That's t equals that. Now, what's 2,000 divided by 1,000? 2, right? So that's t equals 2 over cosine of theta. Now we're actually going to use this expression and this expression in the next part of the equation, or next part of the problem. Okay. All right. Now that we have that figured out, we got to go back and say, okay, well, that's great for horizontal position, but what about vertical position? We need to go up 800 meters at the same time when we go 2,000 meters horizontally. So we have our vertical position equation. I'm going to use h for height because I don't want to use the same letter x because that would get confusing. So I'm going to use h for height here, vertical position, right? H is so it's v naught y times t plus 1/2 at squared. Right, now if this is t equals x over v cosine theta, or t equals 2 over cosine theta, they're both the same thing. So can I replace these t's with a different expression for t, right? We saw for t already, right? These t's must be the same thing, right? They have to be the same t. At a certain t, a certain time, again, I'm saying the horizontal position must go 2,000, and the vertical position must go up 800, right, to hit the target. All right, so the t's are the same, right? So we saw our t before, so I'm going to replace these t's with these other expressions we have. Right? This is called substitution method. You may have done this before. I'm sure you have, probably in your math class at some point. Whether you remember or not is the question, but oh well. All right, so I'm going to rewrite this. So I'm going to have v naught y. Now for this t, I'm going to use this top expression, x over v cosine theta. So instead of plugging in a t, I'm going to write x over v naught cosine theta. Then I'm going to do plus 1/2 of a. We know a is -10, right? Half of that's -5. So I'm just going to instead of a plus sign, I'm going to put a -5 because we know it's going to be a minus, right? Because it's negative. So I'm just going to -5 times t squared. Now for this t, I'm going to use this other expression, the one down here, 2 over cosine theta. And it will become apparent in a moment as to why I'm using two different expressions for the same thing. And there's no real way to know how to do this ahead of time. It just takes practice and experience. So that's just the way it is. All right, so let's keep going. Now we have combined our two equations, right? You may remember we did something kind of like this during our derivations. It wasn't quite this crazy with all the angles and sine and cosine stuff, but we have done something kind of like this before. We have one expression up here. We change it around a little bit, and we solve for one thing, and we plug that expression into a different equation and solve. Okay. So again, it's called substitution method. All right, I'm going to rearrange this a little bit. So I'm going to write this again. H equals, now instead of v naught y, well, what is v naught y? It's going to be v, right, the initial 1,000 velocity, 1,000 there up here, times the sine of whatever the angle is, right? Because there's a sine for the opposite there, right? So I'm going to use that instead. That's going to be times x over cosine, v naught cosine theta. V naught cosine theta minus 5 times 2 over cosine theta squared. Alright, so an interesting thing happens here. These two v naughts actually cancel each other out because they're both referring to the same number, right? They're both referring to that 1,000. So they cancel. And again, I don't know how much you guys remember your trigonometry from algebra class, but sine over cosine is the same thing as tangent. Tangent of an angle equals a sine over the cosine. We have that right here, right? If we multiply this sine by x, we would have sine over cosine, right? So we can replace this now. H equals, and again, this is something you just need to know, right? It's called a trigonometric identity. Hopefully you've heard that. Maybe you've heard that term before in geometry class or Algebra 2. I don't know, but it's a thing. All right, so Google it if you're interested in it. Trigonometry has lots of stuff with triangles, and there's lots of different identities, and that's just one of them, one of the more basic ones. So I can replace this sine over cosine with tangent. So tangent of theta, x. Oh, we get our x there, right? X right here. X tangent theta is going to be equal to minus 5. You know what? Let's just leave this. I'm going to go back to making this as 1/2 a for now. Let's call it g actually, just for simplicity. I don't want to use numbers until I actually have to, you know. So I'm gonna replace that with 1/2 g, 2 over cosine theta squared. Okay, now we're actually kind of getting there. We're getting close. Okay, I've reduced this left side of the equation at least into x tangent theta. Right, and again, we just have to know a little bit of trick with that. Okay, because we know sine over cosine is tangent. All right, I'm gonna go to the next screen now. Okay, so I'm gonna rewrite everything. So I have h equals x tangent of theta minus 1/2 g times the 2 over cosine theta squared. Right? So here I am. What's next? All right. Well, there's another thing, another trigonometric identity that a lot of y'all may or may not, probably haven't learned this one before, but it's just, again, it's just kind of a strategy you got to know about. So when I was doing this problem, I knew there had to be a trigonometric identity to solve for this. I knew it had to exist, right? I was like, it's got to exist somewhere. So I went, and I don't have them memorized. I just looked through them. I was like, what trigonometric identity can I use? And if you go and Google this, trigonometric identity, you'll find there's like, I don't know, like 50 of them or something. And they're all like, 1 over cosine equals this, and like 1 over cosecant equals, this thing. And like there are all these different little ways to kind of convert from back and forth to different trig stuff. So, let's go ahead and square this thing. So let's go ahead and square, this. And we square this, we get 4. So we're going to get h equals x tan theta equals, now look, 2 squared is 4, right? What's a 4 times a half though? Isn't that 2? So the 1/2 times the 4 will be 2. So it's, why didn't we put an equal sign there? Sorry. It should be a minus sign. So a half times 4 is 2. So minus 2g times 1 over cosine squared theta, right? So we've kind of reduced it a little bit. We got rid of that squared sign. So again, what I did was I kind of distributed the squared sign, right, to both terms. 2 squared is 4, but 4 times a half is 2, so it's my 2. And I put the squared sign at the bottom as well, so it's cosine squared theta, right? And when you square a trig function like cosine, you don't square the theta, you square the cosine itself. That's cosine squared theta, not cosine theta squared. Okay. All right. Now from here, I went up and I was like, okay, there's just got to be a trigonometric identity for this, and here it is. And I'll tell you, and I'll show it to you in a second. Well, you can look it up on Wikipedia or something. So it turns out that if you look at the identities, 1 over cosine squared theta is equal to secant squared theta. Right? Turns out that secant squared theta, if you haven't heard of secant before, it's another trig function. There's actually 6 of them. There's the ones you are familiar with: sine, cosine, tangent, and there's cosecant, secant, and cotangent. But anyway, so it turns out secant squared theta is equal to tangent squared theta plus 1. These have all been proven. The proofs are out there. You can look them up if you want to. But take my word for it that this equals that, and that equals this. And so it's kind of helpful to get both things in terms of one trig function, like tangent in this case. So what I'm going to do is now, if I know that through the associative property or whatever, if this equals this and this equals that, then doesn't this guy equal that guy? All right? So I'm going to replace this whole term here with tangent squared theta plus 1. And rewrite my equation. H equals x tangent of theta minus 2g times tangent squared theta plus 1. All right? All right, now I'm really getting close. Okay? Now I'm going to do a weird thing. I'm going to say, I'm going to make up a variable. All right? This is another strategy that, as you advance in math classes, you will start to see. Sometimes equations get too cumbersome to mess with, and you don't want to deal with all these tangents everywhere and all this crap. So what if I just said, hey, you know what? Z equals the tangent of theta. I'll just make it my own variable. Now what can I do? I can replace, anytime I see a tangent theta, I can replace it with z. And it's just a way to kind of simplify things down. So let's rewrite it this way and see what happens. I got h equals x times z minus 2g times z squared plus 1. Right? Now I'm going to actually put numbers in. So now I'm finally ready to put my numbers in. Now, h, we know, is the height, right? So that's the height. That's 800 equals, x was 2,000, right? Yeah, 2,000. Times z minus 2g. G is 10. So 2g is 20 minus 20 times z squared plus 1. So now I'm starting to look like an actual problem that's solvable, isn't it? So now I'm going to distribute the 20 like I would any other time, like this, and then I'm going to subtract 800. So I'm going to end up with 0 equals, let's see, negative 20 times z squared is a negative 20 z squared, right? Negative 20 times 1 is negative 20. I got the 2000 z here. So we got minus 20. And then I did minus 800 both sides, right? So minus 800. So I actually end up with negative 820. Let me just erase that. I actually end up with minus 820 because I did negative 20 times 1 and then minus 800, so we get negative 820. Wow, guys, so what does this look like? We have two of the same term, but one's being squared and one's not, and we have a constant. Quadratic formula setup. This is my A term, my B term, and my C term. I can do this. This is the problem I can do. So let's go to the next slide, and I'm running out of room again. I'm going to rewrite this thing so I have 0 equals 0 equals negative 20 z squared plus 2000 z minus 820. So again, my A term, my B term, AC term, so hopefully you remember the quadratic formula equation. This is going to be z equals the opposite of b plus or minus square root of b squared minus 4ac divided by 2a. Alright, so we're going to plug our numbers in now. So we're going to have z equals opposite of b. B is 2,000, so negative 2,000 plus or minus. We're going to get two answers here, right? Because it's actually two angles that will work for this. Square root of b squared. B squared is 40, or 4 million, I think. So it's 2. So let's just solve the whole thing underneath the equation at once, right? So let me pull up a calculator. Real quick. Alright, calculator. So let me go scientific mode here. Alright, so I'm going to do b squared, 2,000 squared. Whoa, I squared it twice. I squared it twice, I squared it once. Okay, 2,000. Try that again. 2,000 squared. Enter. Alright, that number minus parentheses 4 times a, which is negative 20. I don't know what this calculator is doing. This calculator is dumb. Let's try this again. Let's do the 4ac part first. So 4 times a negative 20, so I do 20 first, and then the negative sign, I guess. There we go. Okay, so this calculator is weird. Times c, which is negative 820. So negative 20 negative. Right? I'm going to add that to, no, subtract that because it's minus 4ac, right? So minus, actually. That number, let's write that down. So it's 65,600. So under the square root we have, it's going to be 4, or, sorry guys, I hope you all are sorry to make so many little minor errors that add up, and I'm sorry, but I'm just, you know, this problem is kind of a pain in the butt. So b squared here minus, what was that number? 35,000, no, 65,600, right? 65,000. 65,600. Okay, so we can do that. So it's going to be, so it's going to be b squared, which is 20,000 squared minus 65,600. And what's the square root of that number? So square root that, and I get, what did my calculator just do? See, it's doing these weird things. I don't know what it's doing. So use your own calculator. This one on my computer is really, really bad. I don't like it at all. So I want to use mine. Okay, you use yours. And I'm getting, let's try it one more time. 20,000 squared minus 65,600. And I square root that number. And I'm getting a number very close to 2,000, actually. I get, actually I should be getting, I'm getting numbers a little, I think I messed up in my calculator. So let's double check this. So on your calculator at home, okay, on your phone or something, let's try this again. So C is negative 820 times A, which is negative 20, times 4. So yeah, that's right. All right. So B, oh, B is 2,000. I was squaring 20,000 the whole time. No one said anything. 2,000 squared, not 20. I was 20,000 squared. I hope you all caught that. And we're like yelling at the computer screen. What are you doing, Mr. Chen, you idiot? It's 2,000. All right, sorry about that. So 2,000 squared. Jesus. No wonder this is so weird. All right, minus 65,600. Square root of that number, and I get 1,983. All right, so under the square root we have z equals negative 2,000 plus or minus 1,983.5 divided by 2a. So a was negative 20, so 2a is negative 40, right? Let's double that. All right, so we're going to do z. It's going to get two answers for z. So I do negative 2,000 Let's minus first. Let's minus 1,983.5. And then divide by negative 40. And I get 99.58. 99.6, we call it. Alright, 99.6. And my other z value, if I do the plus now, so negative 2,000 plus 1983.5 divided by negative 40, and I get 0.4125. So it's 0.4125. Okay. Those are not my angles. That's a z, right? Remember, we said, earlier we said z equals tangent of theta, right? Ooh, so this isn't the angle, this is what tangent of theta equals. So how do I solve this? Well, tangent of theta equals 99.6. How do we solve it? See, if you recall in class, we said if you don't know the angle, but you know what it equals, you can do the inverse tangent. So we do the inverse tangent of 99.6, and that will give us our angle. So, plug in our calculator. Alright, I'll give it a shot. I'll try the scientific guy one more time. So let's try that. Just so you can follow along. So now we're going to do, alright, inverse tangent isn't even on here. Cool. How do I do inverse tangent? I don't know. How do I do it? Can I do it? Can I do it? Can I do it? Not gonna let me do it. Alright, screw you, calculator, you suck. Alright, whatever. Okay, on your calculator, so it's on the, if you have a TI-83 or whatever calculator you're doing this on, hopefully your phone has this function. It's tangent with a -1 sign above it. Or you can do 1 over tangent, the same thing. So I guess I could have done that. I'll do it that way. I'll do it that way. Alright, I'm starting to get delirious. Okay. Alright, so 1 over the tangent of 99.6. And see, how do you use this to punch this in? This is so stupid. This calculator is dumb. I hate it. I hate this calculator. It's very bad. So we'll do 99.6. And then I do times 1 over tangent. I don't know how I'm supposed to punch this in. It's so weird. That ain't... Okay, I don't know. Am I in degree mode? I can't even tell. Dude, screw this calculator. It's a piece of crap. I hate it. Alright, I'm gonna do it on here. Okay, you do it on your calculator. I think the phone has this function. See, I can't do this calculator. I can't deal with it right now. So I'm gonna do second tan. Second tan, 99.6, and I get 89.42, which is the correct answer. So the first angle I get is 89.42. So that's almost straight up in the air, right? 90 degrees is straight up. So this is like just barely tilted, not straight up. I mean, it's almost straight up in the air. So it's going to go so high, and then as it's going really high, it's traveling slowly to the right, and then finally it's going to come down later on, right? So next we'll do the tangent of theta. This equals, our other number was 0.4125, so 0.4125. Inverse tangent of that, 0.4125. We'll give us our other angle, and we punch that in our calculator, and we're going to get 22.4. 22.4 degrees. Alright, there we have our answers, and whew, pain in the butt. Sorry for all the little erasings and stuff. Hopefully that you're able to follow along kind of on your own if you even made it this far. If you did, great. In fact, I get a little bonus. If you tomorrow or any time in the next 2 weeks come up to me and say the word what should I make the secret word be? Say the word it's got to be a weird word no one can just randomly say in conversation, right? So what could be a weird word? Oh, say the word magnetar. Magnetar. It's a special kind of crazy astronomical thing. You can look it up if you're curious, but magnetar. Say the word magnetar to me, and I'll give you some extra credit. Alright. Thanks for watching the video, guys. Sorry, that's an hour-long video. Wowzers. Alright, so again, hopefully you didn't have to watch the thing straight. Hopefully you skipped around and did what you want to do there. Wow, I'm going to bed, so have a good night. I'll see you all tomorrow. Bye-bye.